program, many things can usually still go wrong. Like, we say a cosmic ray can hit your memory and a bit flips. That can happen. Well, maybe you can use some servers or clouds and so on, and then when you use remote machines, there are administrators with physical access, so they can do bad stuff, and or the machine itself might have bugs, and a cat might break a cable or pull out a cable or stuff like that. So there are many other uninteresting reasons for program errors. But, well, a single cosmic ray particle, whatever, cannot probably break the Ethereum network because that can only affect one node. And if that, I mean, for cosmic rays to cause a serious trouble, well, thousands of particles must arrive at the Earth, and they need to hit simultaneously the same memory cell in many different machines and so on. So Ethereum is kind of resistant to many uninteresting features. So bug-free programming makes sense in Ethereum. Let's aim there, because in other places, before you remove all bugs perfectly, your weakest link is no longer programming errors. There are some other non-interesting reasons but to worry about. But in Ethereum, you can still, well, it's really difficult to get other weakest links. So here my aim is to match what happens and how a program looks. And yes, I have to talk about what happens in Ethereum contracts. This is just one mental model. It's just one way of thinking about it. But, well, something calls your Ethereum contract first with an input, and yes, your contract has some state, and something happens, and an output is produced. Okay, well, this something might contain calling other contracts or sending in or whatever, but an output comes out, and, well, there will be a contract state after the call. Are there Haskellers or category theorists here? Wow, cool. Yes, greetings, I stole your ideas. And then, so this is my mental picture. So, and I translate that literally into program syntax. So on the left, this is what my contract here should do, where it starts as a contract A, and when somebody calls function f, I want to call function f, that's the input. When that input comes in, 0 is returned, and it becomes contract B. And when it's called again, it returns 1, and it becomes contract C. When contract C is called, it returns 2, and it becomes contract A, and so on. And that's kind of literally reproduced here as a text. And well, when the contract A is called with F as the specifier, then it returns 0 and then becomes B, and B returns 1 and becomes C, and C returns 2 and becomes A. That's kind of straightforward. And then, well, so I did it with 3 different states, but that's a very small state space. Well, maybe a contract should hold numbers. So when you call it, each time you call it, a counter increments and it returns the previous counter number. That's kind of implementable. So instead of having just one alphabet A, B, C as a state, I put some argument after the name of the contract. So, well, now the contract signature looks like, well, the name of the contract is A, and it's accompanied with a number. When it's called, it returns the counter value, and then it becomes A again, but with an incremented number. That's my program, and then it behaves like this. So it returns bigger and bigger number each time it's called. So the syntax, So before I invented this syntax, I knew the syntax of Erlang and where you can write something similar. So it's certainly influenced by that. And an Erlang process and a smart contract is kind of conceptually similar. So it's not a bad idea, I thought, 1 year ago. Many Ethereum contracts define games. So well, here I'm showing states for a contract called Vault. It's like a wallet, it's your personal wallet. But the problem it's trying to solve is, well, somebody might steal your private key. So the solution here involves 2 different kinds of keys. One is called the vault key. The other is called the recovery key. By the way, this idea comes from IC3 people, and so it was an example for a new Bitcoin script primitive, but well, from there, people implemented in Ethereum and so on, stuff happened. I'm taking these ideas. So the vault key is your usual key to get your money out of the wallet. You can call unvault function with your vault key, and then your contract enters a special state. You have to wait for like 2 weeks or 4 weeks, some amount of time written in the program. And then after that, you can call another function called redeem, and then a payout happens to the address specified in the unvault call. Why delay 2 weeks? Because, well, when somebody steals your vault key and calls this unvault, well, you can check the contract every week. And then if somebody else is trying to get your money, you can reach your more important key called the recovery key. And you can call recover, and you can cancel this unvault call. And moreover, you can change this vault key, so you can create a new key as your new vault key, and then the attacker cannot do anything with this old vault key anymore. So that's the idea. And then, well, when you are really, really unlucky, the attacker can steal both keys, vault key and the recovery key. Then what would happen is both parties try to withdraw the money, but both parties keep canceling the other party's request. So that would become a stalemate. To make it explicit, there is a destroy method. And when anybody with the recovery key calls the destroy method, the contract enters the destroyed state, and from this destroyed state, nobody can get anything out of this contract. This kind of cancels, or this nullifies the incentives to steal any of these keys. At most, I mean, if you succeed in stealing both keys, you will probably get nothing. That kind of chases thieves away. That's the idea. When you implement it in Solidity, you can do that. And then you want to check if this contract, if this code matches the state diagram I drew. For checking that, first I have to identify what Solidity state correspond to the states in boxes in the state diagram. So well, in this case it's easy. Well, there are only 3 states. When destroyed Boolean is true, it's destroyed. Otherwise, when this unvaulted amount is 0, it's the normal state. If this number is not 0, it's the unvaulting waiting state. This is not hard, but it certainly requires certain human judgment. And then, well, after that, actually, after that, everything can be done kind of automatically because this involves no loops. But for doing that, okay, first you have to look at the constructor. Okay, well, it returns the usual state, not to any other state. That's good. And then you have to read the rest of the program 3 times because starting from the usual state, well, which function can be called, you have to check all interface functions because anything can be called anything can be called on any state by default. So you have to check whatever happens from each state for each interface function. And then, well, when the default function is called, the state doesn't change. So from usual, it stays usual. That looks okay. When unvault is called, so the state can become unvaulting. But if the argument amount is 0, it can stay in usual. That's not drawn in the state diagram. So I put a question mark. And then if you, well, when redeem function is called, well, it doesn't do anything. And then when, no, it does something. It does something. Actually, it sends you, no, it sends some 0 amount of ether to somebody and becomes usual. So it's again questionable behavior. And when recover is called, well, no, it doesn't do anything, so that's good. And well, when destroy is called, it becomes destroyed. That's good, as specified in the diagram. And I have to do it like 3 times. When the contract is in unvaulting state, that means destroyed is false and the unvaulted amount is not 0. Then yes, you can call this unvault again. Well, no, okay, well, you can call the default function, that's fine. You can also call the unvault function again. That was not drawn in the diagram. Is that fine or not? I have to think again. When redeem function is called, well, yes, this can become usual, that's fine, as specified. And when recover is called, it goes back to usual, canceling this waiting request, that's fine. When destroy is called, it becomes destroyed, that's fine. And then the rest is kind of easy because every interface function is prefixed with this modifier, not destroyed, not destroyed. So the call is aborted, nothing can happen from destroyed. That was the easy case. But anyway, I had to read the program 3 times because the state diagram had 3 boxes. That's not efficient. So essentially, viewing a program takes at least the number of states times the number of lines. This is not only for human reviewers, but also for any automatic methods. That's not good. And when you try to check the same thing for a Bamboo program, it's easier, that's my claim. Well, you have 5 arrows in the state diagram, and you have 5 become phrases in the program. So essentially, you need to check which one corresponds to which, and from the usual state, there are 2 arrows going out. One is going to unvaulting, the other is going to destroyed, and yes, one is going to unvaulting, the other is going to destroyed. From the unvaulting state, there are 3 arrows going out, and yes, there are 3 becomes phrases. So it's much easier to check that the program corresponds to the state diagram. It's kind of cheating because I chose this format of presenting states and I chose this syntax of writing programs, so it's kind of obvious this is certainly achievable. The more interesting thing is how far I can keep this discipline when there are more and more users, they want more and more features, and along the way, how much I can keep this kind of discipline, that's the real challenge. But I needed to write something useful, so I'm already adding some features. I don't like that. I generally don't like to add stuff to this world which is already a mess. But I wanted to add features, so sometimes I wanted to call other addresses on the Ethereum chain, but I didn't want reentrancy. So currently, whenever you call something, you have to specify what happens in reentrance, in case of reentrance. And currently, only abort is supported. So whenever your contract calls something and that thing calls back, that aborts. Eventually, I want to write something else here, but I'll think about it later. You can create a contract. That's a deliberate choice because I wanted to keep each instance of the contract simple. So I think I need it soon. I added arrays. I wanted to implement the ERC20, and it's kind of, it seemed necessary to add some kinds of arrays. I didn't like that because here you have an assignment. You can modify a particular storage location here. I don't like this at all. When you don't have arrays, Bamboo has no assignments at all because everything in the storage just appears in this becomes phrase. Here I'm introducing side effects. I don't like it at all, but okay, well, people want to use tokens, and the tokens are kind of essential feature to implement crypto economic mechanisms. So I'm not quite happy. I'm not completely happy about adding this, but I did. What's missing and the priorities? Language specification and an independent interpreter. These come first because whenever I have a chance, I keep complaining that the Solidity program has no meaning until it's compiled into EVM bytecode because Solidity has no specification. You know, it has a documentation, but it doesn't tell you if your program is executed from top down or bottom up. If you believe it's executed from top down, you are just, imagining that, and you don't know how many other things you are just assuming. So I say this always, and this applies to Bamboo as well currently. I'm not happy, so I'm writing a language specification, and also an independent interpreter. No, this one is not in progress. Language specification is in progress. But okay, well, if I learn the K framework, I can do this at the same time. So maybe I should just talk to these guys. I don't want to add many features soon. Maybe the most prior one is calling externally defined contracts. Once this is done, the language is kind of usable. So maybe I should delay this until the other parts are done. So here's a famous phrase by Simon Peyton Jones: avoid success at all costs. Yes, I stole this phrase from the Haskell community. But this is kind of ambiguous. Success at all costs, avoid at all costs. I haven't decided yet. Here's how you can help. If you write OCaml, please talk to me. Thank you very much.